Okay, uh, now let's continue from the point where we have stopped. I finished the F matrix definitions and the properties, the mathematical model to analyze the epipolar geometry of a multi-view imaging system with interesting properties, and it is for completely uncalibrated cases where calibration matrix is not known. But we also understand in the last point here, I can obtain a projection matrix for using some canonical form like identity and zero. The world coordinate system is one of the camera coordinate systems, and the other projection matrix camera is written in terms of an F matrix, but the epipolar point, okay, and an arbitrary skew symmetric matrix. Please note when I say arbitrary, therefore this given an F fundamental matrix in an uncalibrated scene, you cannot obtain the projection matrices, okay? It's a unique form. But from the projection matrices, as I have explained here, from the given projection matrices P and P prime, from the pseudo inverse of P and the P prime and also the epipole, you can obtain uniquely the fundamental matrix. Now let's come to the triangulation part, the last part of the course, where we will reconstruct the scene. Once again, we are talking about linear triangulation. The interesting thing is we have points here. We have already obtained the fundamental matrix or a projection matrices, okay, using either calibrated or uncalibrated. I can say that unknown x projected to the small x and the same unknown x with respect to one coordinate system, maybe this point, it will be projected with the other imaging system to the x prime, like x and x prime here and here. And one interesting thing to note, x times x cross p of x is equal to 0, okay? Hence, we can obtain these relations. One of them is linearly depending on the other two. Therefore, I just only take two of them. And finally, I obtain such a relation using two equations from here and two equations from there in terms of the projection matrices, P and P primes, the first, second, and the third rows, okay? And the corresponding xy and x prime, y prime coordinates of the pixel locations, okay? Therefore, using such a relation, I am able to obtain an A matrix with known, everything known here. And I have an unknown x vector, capital X, capital Y, capital Z, and 1, homogeneous coordinates, 4 by 1. This is 4 by 4. And hence, I can have, try to solve such a simple solution. I can have sometimes, or due to noise, ax is equal to 0 is not completely exactly satisfied. Therefore, you prefer to have ax magnitude square to be minimized rather than exactly equal to 0. But obviously, x is equal to 0 is a trivial solution. Therefore, I just put the extra constraint magnitude x is equal to 1. Therefore, as we did many times in this course before, the x is equal to the eigenvector of the smallest eigenvalue of A transpose A. Therefore, you go and calculate A transpose A, which is a square matrix, and you find the eigenvalues, 4 eigenvalues, and the smallest one, and the corresponding eigenvector is your solution, the 3D point, okay? Therefore, an interesting point here is, maybe you see only 2 images at this point. I can say that there could be 5 images just like this, looking to the same x, but 5 different projections. All the projections are estimated through F matrix, E matrix, calibration, whatever. Then you can just put 2 by 2 every point. If there are 5 images here, you can put, for example, 10 such lines, and solve it using this criteria, and you find the, again, such a technique will give you an estimate of this. One can say that since they are not crossing, these rays are not crossing, our solution is something in between the nearest points between these two rays, okay? Now, if we extend this to another solution based on a geometric triangulation, this time I will do a little trick here. Since AX is equal to 0 is not exactly satisfied, possibly, how about determining or trying to find some image points nearest to our measurements such that this new image points exactly satisfy the relation. In other words, let's assume this X is measurement. You just use Harris corner detector, you obtain this point. There is another point, Harris corner detector finds this one. Due to errors, they are not exactly in the same position. The real point in the scene, in fact, projects to here and projects to there. And what I'm saying is this. Let me try to minimize this D, this distance, and that distance, D prime. Let me minimize their squared sum, for example, such that I can find these new points x cap and x cap prime, which is exactly satisfying the epipolar constraint. Therefore, I'm writing a cost function. Those cost function is between the measurements and unknown points. Measurements and the unknown points. But these two unknown points, they exactly satisfy the epipolar constraint of F. Okay? Therefore, what I'm saying is, hey, let me try to find x cap and x cap prime. I can find their 3D depth very easily with the previous technique in the previous slide. But my points x cap and x cap prime are something in the neighborhood of x and x cap, x prime, and also they exactly satisfy the 3D point. Okay? Therefore, the trick here is, since they exactly satisfy, those x is generating a L prime on the next image, and the x prime is generating an L, okay? Therefore, this is generating an L, okay? This is generating an L prime. X cap prime is generating L. And what I'm saying is this, therefore, let me go and try to minimize the measurement x and L, which is obtained due to fundamental matrix epipolar geometry. Okay? Therefore, this is the minimum distance, hopefully, to the epipolar line of x cap prime. Okay? Therefore, x cap prime is here. It is generating our epipolar line, which is nothing but this here. I hope you can see me. This is your epipolar line. And I'm just finding the minimum distance. Now, if there is a longer solution to that, you can have a function which is a polynomial of sixth order. By doing some tricks, mathematical tricks, at the end, you were able to obtain your epipolar lines and the corresponding x cap and x cap prime. Once again, by solving this, you exactly find this point, and then we simply find, using the previous technique, this linear transformation in the previous slide, you just triangulate and find your solution. Okay, there are two solutions. One of them is more algebraic, the other one is enforcing the projections of a perfect point, which is generating your in the neighborhood of your measurements, the exact projections. Okay. Now, one important thing to note at this point is the ambiguities. Right now, I obtain using two cameras, either with a given calibration matrix or without a calibration matrix. We were obtaining some results. Now, assuming my calibration matrix K and K prime is given to me, which means from the estimated polar geometry F, I can obtain E matrix. From the E matrix, I can decompose R and T. Let's assume I have all these things. But still, we have a problem. The 3D structure, XYZ points, and the translating component between the two cameras, the baseline between the two cameras, they are obtained up to an unknown scale. Let me mathematically explain. In other words, if you have this one or that one, maybe 5 times larger, this one, 2 times larger, and the points are 3 times far away or nearby. What I'm saying is this system and that system exactly give the same point correspondences. They exactly give the same point correspondences, but the resulting 3D reconstruction or the 3D translation can only be obtained up to a scale. Let me explain why it is. First things first, let me remind you one little thing. In the past, we did these things. An XYZ projected using such a 3x4 matrix, typically in terms of the focal length, for example, if you multiply your homogeneous 3D point by 3x4, you obtain something in 3 dimensions, homogeneous in 2, okay, it's in P2, in other words. And what I'm saying is this, since in homogeneous coordinates you divide by this Z, you obtain perspective projection. That was the trick. Therefore, if somebody gives me a vector here, A, B, and 2, for example, I realize that if you don't observe 1 in the last column, whatever I observe, it is due to the Z. Okay? Therefore, the vector here, the last element is your Z point, the distance from the origin of your camera coordinate system. Okay? Therefore, let's assume, let's start. If I start with this X, Y, and 1, I'm just enforcing right now with starting with 1. Okay, if X is equal to P of X, and P is a canonical, in other words, it's selected as the world coordinate system with a calibration matrix K, this is conventional. Now what I'm saying is this, if you simply multiply X, Y, Z, 1 with this identity and 0, the last element will disappear, and you will obtain something K times X. Okay, therefore, I'm saying this. Therefore, if you multiply this thing like here, K identity 0 and X, Y, Z 1, the result here is K times X, Y, Z. Okay, because the last one is multiplying with the 0 here, and you will only obtaining this one. What did I write written here? It was X, Y, and 1. I started with that one. And what I'm saying is this, as soon as you take the inverse, here, okay, you will obtain your K inverse, okay, your K inverse multiply with your X, okay, your X, Y, and 1, okay, to be able to obtain X, Y, and Z here, okay, you have to have including this Z inside here, okay, therefore this Z is due to this Z over there, okay, this is as soon as you obtain your Z as a result of this thing here, therefore let's try to project this point X, Y, Z onto the other view. In other words, this point I am projecting to here, the second image. Now X, Y, Z is equal to this thing, therefore let me have, this is my projection, K prime is the other calibration matrix, R and T is the pose between two cameras, therefore the X prime is equal to P prime times X, and Now, if I write this thing to here, instead of P prime, I write K prime RT. And instead of X, I'm gonna write, be careful, instead of this X, now this is your X prime, which is K prime RT. Now, there is something here and 1. This is the last element, it's 1. And I'm gonna write this guy to here. Now, if you multiply this whole thing by this part and this one, and obviously this one and that one with this guy, the result will be nothing but this one. Okay, therefore let's do it together. K prime r, then here z is a scalar, I write it here. Then I write K inverse, and I obtain nothing but my small x. Okay, this is my small x, and then plus K prime, this K prime, then T. Okay, I obtain this thing. Now, in the other side, I have again the 2D. The other point here, if I simply divide, this is homogeneous, therefore I can divide everything into with Z, I obtain K prime R K inverse X. This is X prime, still homogeneous, dividing by doesn't matter, and you obtain K prime T divided by Z. Now, this is the crucial part. Okay? This is a ratio. The ratio says multiply your t by 2. If you multiply the z by 2, the 2D projections don't understand. The 2D projections don't change. With the same 2D projections, you can obtain any kind of solution where t magnitude is 1, 10, 100, because you can multiply with 1, 10, 100 all the z values as well. The structure will be 10 times larger or 10 times smaller. You can play with the t and you get exactly the same point correspondences on the images. That's a very important result, which means it says, okay, it says it is impossible to get absolute scale of the scene and the translating component by taking images of a scene from 2 views or multiple views. Now, I just want to emphasize this important fact once again. Please don't ever think by using your mobile phone, taking the images of your anything from 2 views. You can reconstruct it, this object, but up to a scale. You never know how much you translate between the captures of the images during this instant. The only thing you can have is a correct translation unit vector, maybe showing the correct direction. The 3D structure is obtained, but with an unknown scale. Maybe it's a toy, maybe it's a huge architectural building, I don't know. But at the end, from 2 views, this is the only thing you can obtain. Okay, now there is more ambiguity. Look at this. Look at this equation. I have x is being projected by p and obtain the projected value small x. If I multiply 1 over k scalar and the k here, certainly they cancel out. This is exactly equal to each other, but this is, k is 10. You are, for example, making your small toy image 10 times larger. And then inserting your k to here, you are making it smaller. The translating component, for example, can be small, and your observed x's don't change. Okay, you are not simply obtaining any different image measurements, but your structure, and maybe the structure is no more a little toy, but it's a huge thing, but it gives the very same image. Okay, and you can make it more general. How about this? Px, put a Q inverse and Q here. Obviously, This is a 4x4 transformation. As the projectivity, taking an x vector and the homogeneous coordinate is converting to another homogeneous coordinate. And Q inverse Q is identity, therefore it doesn't change anything. But if you put Q to X, if you put Q inverse multiply from right to the P, this is another projection matrix, and this is another 3D coordinate in homogeneous world. Your X don't change. Your image pixels are exactly the same. Whatever you are doing, if you don't have anything about calibration, E matrix, rotation, translation, if you have simply F matrix, from the F matrix you can obtain projection matrices as a skew symmetric multiplication. I've explained it before. Therefore, this is what it says. Therefore, your results could be not correct. You can obtain your 4x4 projection later. You can first estimate your Q, then you can have some ground truth 3D points. In other words, you can have like something like this. Maybe your box is a little bit exaggerated, but you go there, you say that, hey, this point is 1 meter, that point is 2 meters, this is 90 degrees. Then you look for a Q. You look for a Q so that this kind of a projective reconstruction will be corrected by a Q matrix. Okay, this is the Euclidean Euclidean coordinates. Maybe you know a priori. In practice, not necessarily. But if you know it, then you can obtain a Q matrix. Therefore, you come here, you solve your result, then you look for your Q matrix and multiply Q and Q here, Q inverse here, and you obtain your perfect results. Now, let me show you this. This is a perfect, beautiful 3D scene. These are the points I obtained, okay, projections. But I realized that I can have two other images, exactly the same pixel locations, but the 3D structure is degraded, transformed using this QP. You make this beautiful cube, such a structure. Your focal lengths are changing. Your principal points are changing due to this Q inverse. But the only thing doesn't change is you obtain the same pixel positions. I gave you this. Some people will generate me this result. Some people will generate me this result without an extra information, anything about the calibration matrix, just from the fundamental matrix, uncalibrated reconstruction. This is a typical result. From such two images, these are your results. Okay? Now, how did you obtain this? This point is obtained, that point is obtained. Manually, people are just merging these things to show that, to make it visible for you. In other words, the point here and the point here in pixel coordinates using triangulation from a projection matrix obtained through F matrix. This is the result. This is the result. They are completely warped, morphed using an unknown Q. Okay? If you have your Q, if you enforce them to be like a similarity, okay, a transformation 4x4, but this time not 15 completely arbitrary numbers. We have some fixed rules for that. There is a rotation matrix inside. I'm going to explain in the next slide. If you have that case, therefore, you can have the same cube for similarity, not Euclidean, unknown scale, you will have this kind of a result, okay? In fact, this is the case I'm talking about with the scaling ambiguity previously. Even you know the calibration, the translation and the 3D is always up to a scale. This is this case, okay? And you cannot beat this. Even you have calibration, you will still live with this case. Now, this is a typical result from such a 3D image scenario, previous images. You reconstruct this with unknown scales, maybe here and there, and this is a visualization at the end, putting the images intensities of those previous images on this roof and on this flat surface so that it's visualized beautifully. Okay, how about our 3D transformations? This is our Q, completely arbitrary projectivity, 16 numbers, 15 degrees of freedom due to up to a scale transformation. Okay, affine, A is 3 by 3 arbitrary, T is arbitrary. Therefore, you have 9, 3, 12. Here, rotation, 3 degrees of freedom, 3 translation, 3 degrees of freedom, with similar scale, 7 degrees of freedom, and finally, the Euclidean transformation. Okay, these could be the transformations, but if you deal with projective reconstruction, you are dealing with this. But if you insert your calibration matrix into the problem, you are dealing with this kind of a scenario. Okay? Therefore, if you don't have anything about calibration, you are doing a projective reconstruction. You can upgrade your reconstruction to affine similarity using some tricks. Therefore, it is also possible even for the cameras whose calibration information is not known, it is possible to obtain the reconstruction step by step from projective to affine, affine to similarity, and like that. Now I come to the last point where until now I was using two views. I did many things. I have the calibration matrix. I have the E matrix, F matrix. I did many things. In real life, in practice, I don't stop with taking two views for reconstruction of anything. I prefer to deal with at least n, that red n images. All of them have maybe m points inside. There are m fixed 3D points. These red dots are m, and this is n. Okay, therefore 1, 2, 3, n different images, and obviously n projection matrices, P1, P2, Pn, and there are m fixed points, 1, 2, 3, capital M, blue. And our problem here is, I want to estimate the projection matrices and also the n projection matrices for each view, and also the 3D points, xj, using small m correspondences, m points, total. If you just relate them each other, this point is this correspondence, this point is this correspondence, for example. If you make these correspondences, there are n times m correspondences. These small xij's are pixel points that I obtained. I don't know the poses. I don't know the 3D points, okay, of capital M. And I'm trying to find this thing from not two views, but n views of the same problem. Obviously, I'm expecting a more robust solution through such a scenario. Now, I'm going to explain shortly a final algorithm to do it. But let's assume using pair by pair, I obtain P1, P2, P3. I also obtain X1, X2, X3. Okay, therefore, what I'm saying is this. I have these things here. 1 point, 2 point, 3 point. This is one of them. This is the other one. This is the last one. Okay? As you can see, my aim is finding the 3D points here, the unknown rotations, translations in between. In other words, the projection matrix 1, P1, okay? The projection matrix P2 and the projection matrix P3. That's what I'm trying to obtain. I'm going to have a single cost function. I'm going to have a single cost function. From the single cost function, the correspondences will be tried to be matched with the unknown 3D points projected with the unknown projection matrices. These P and X points are P projections are XJs are unknown, but as soon as you multiply them, you obtain these things as your points, fixed points. As you can see, these blue points are measurements. They don't intersect. They are erroneous. They are not precise. But these points, the red ones, beautifully satisfy projections. Hopefully, they are nearby. Okay, they are nearby to these things. Now, bundle adjustment is an algorithm from a given initial a priori assumptions, estimates that you obtain through F matrix, E matrix, whatever, triangulations that we have learned. From them, I am globally, as a whole, solving, minimizing a cost function such that all the reds try to get nearby to the blues. You are playing with these things. You are playing with the focal length and everything. You are playing with the rotations translations such that at the end, the red projections that you obtain through here, P of X create the reds, P times X creates these reds. These blues are measurements. They are fixed. They get nearby through this cost function. This is called bundle adjustment. Reprojection error. You reproject your 3D estimates and you try to minimize with the measurements that you obtain. Okay. If it is a Gaussian noise, I can show that, or one can show that it's a maximum like estimation of these P and X. I try to estimate these things with respect to P and X. Okay. Now, it's a huge problem. Maybe 1,000 pixels, 100 cameras, okay? And as you can see, 1,000 by 100 is 10,000 matches that you are trying to minimize. Now, I'm going to write it like this. Everything, all your 3D points, these are X3D. Also your rotations, translations, all of them as a huge P matrix. This P matrix, this time, it's a huge vector. This is not a matrix, it's a vector. This P vector is consisting of everything unknown, okay? And this capital X is your X11, Y11, X12, Y12, all the measurements. These are measured. I'm sorry for that. These are measured, and these are unknown 3D plus pose. Everything here. Now I'm trying F matrix. The F function is projection, okay, which is a nonlinear operation maybe. Because you're obtaining a single vector at the end. Therefore, it is making a mapping. Please note, these are huge vectors, okay? And you try to minimize this cost, which is nothing but this difference, the difference between them, and you minimize with respect to P. Now, how to do it? Either Newton iterations or something called the Levenberg-Marquardt. I'm going to try to explain it briefly. The Newton iteration for bundle adjustment is a Taylor series expansion. This complicated function of mapping is at point P0 plus delta. This is your initial estimate. This P0 is maybe due to, there is a P0 plus a delta. This is your real estimate. You will estimate it. This is due to E matrix, pairwise, whatever. This is this little delta you are trying to obtain. You will make an approximation here, first order. Therefore, you try to be near the correct value, the global optimal P point. Now, is P0 plus delta, you can approximate it using Taylor series expansion where Jacobian is nothing but this partial derivatives. In other words, let's see what is this partial derivatives. With respect to a component of this T, you are saying how they are related. The Jacobian is doing this. The Jacobian says play with the second translation translating values. Your second point projection will be affected this much. Okay? Therefore, this Jacobian is this information. This is a standard Taylor series. And P1 is your next estimate, P0 plus delta. Therefore, what you do is you write P0 in terms of this relation. You subtract x minus P1, but P1 is written like using these two terms. And this difference, that difference is your current estimate based on your initial estimate. Fp0 is your initial pose and 3D projected, and this difference is called E0, and J delta is your correction. You are trying to minimize this. One can show that this is a least square solution as before. Pseudo inverse of J times E0 will give you the delta. This delta is note again, update in the 3D structure, update in the pose on top of P0. And this pseudo inverse can be written in this form. Okay, therefore I obtain the delta and you insert delta on top of this iteratively coined. Now this assumes such an approximation is correct. A quadratic approximation is correct, okay, and this is called the normal equation. The Levenberg-Marquardt is an extension to it. Please note this is the tricky part while you are dealing with this is your E0. This is the step, and you are trying to put this by using an inverse operation, put this one to the other side. Okay, this is while you are doing least squares, this is how you do it. These are the normal equations, but this matrix sometimes is not very reliable. Its inverse doesn't exist. Then you make a little trick. Instead of this, J theta J, you plus add the diagonal terms like D1, Dn, and these diagonals are obtained from J transpose J. And these are 0. This is a diagonal matrix here. Obviously, these diagonal matrices have inverses. Such a term, adding this, makes a guarantee that you have an inverse. And maybe more interestingly, if you increase lambda a lot, you will have which will be nothing but that will be, if you increase this, that will be negligible, and you start looking like a gradient type of relation. Hence, the trick becomes you at any point you apply this and you try to find the inverse. You find the solution. If there is success, which means your error is decreased, which means your Taylor series expansion is okay, then you make this smaller, you get rid of this, and you become more like Newton's equations. Okay, the previous Newton iteration by increasing this term. Okay, you therefore use make it. This is smaller. That term is getting smaller. This term becomes larger, or it is becoming more effective. Hence, you obtain something like a Newton iteration. If the approximations are not good, Taylor series expansion is not a good approximation, then your error will not decrease. Then you increase this, you make this part less useful, you make this part, okay? You make this part less useful, and you work like a gradient descent type of relation, and then, which is guaranteed to decrease. This will make you faster, very quick convergence. The other one is guaranteed. Therefore, increasing and decreasing the lambda, you can obtain good solutions for your bundle adjustment. There are other tricks, sparse bundle adjustment, because note that your typical solution is it's a very large matrix. The Jacobians are very large. Therefore, you have to deal with this to make it faster. You have to do this as a sparse bundle adjustment, but this is beyond our scope. This is how we deal with the bundle adjustment of the final solution. Until now, we learned many things. That very final slide will be a summary of the things that we have learned. Maybe you're asking to yourself, I will learn many things. How should I approach if I would like to have a 3D reconstruction of anything from my mobile phone? Let's do it. For the initial views, take two images, view 1 and view 2. Please note, first make your calibration of your camera, okay, using a calibration pattern. Find your K matrices. Find the view 1 and view 2. Find the extract and the match features using orb, Kaze, Sift, whatever you like. Match them. Solve for F matrix. Normalize 8 point by Hartley. K is available. Decompose. First find E matrix from F, K inverse, and K multiply left and right. Then decompose R and T. Now you have everything available. Make triangulation. Linear algorithm is okay. Or the other one, the optimal one, sixth order, you can work it by yourself if you like. Now what do I have? Two views, some matches, and the 3D structure up to a scale. Now, for every new thing, let's do it together here. View 1, view 2, match, 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 match. Like this is a, I don't know, this is like a 3D structure here, something like this, and you obtain this one. Now the next step is tricky. I don't have to deal with the E matrix anymore. Take the third image, find the correspondences. This goes to here, that goes to here, that goes to here, that goes to here. Maybe this point is here as well. That point, these are completely new. Okay? Now, interesting point is this part. I have X, Y, Z here, and for all of them, okay, I think the drawing is not very well, but whatever. Now I have the 2D points, X and Y here. I have the 2D points. Therefore, X, Y, Z here, X, Y here. Because I know that they are connected. I match them. This is matched to here, this is matched to here, and this is matched to here. Okay? Therefore, I can find 3D known, 2D known. I have an algorithm for that, PMP, or anything else. Therefore, I got the pose between these two. Okay? I got the pose which pose, if this is with respect to this coordinate system, this is your current origin, I can find the rotation and translation using P and P, okay? Because knowing x, y, z with respect to this coordinate system, model coordinate system we call it, and those points here, which are connected to the previous ones, I can find the rotation and translation between, with respect to the model or world coordinate system, the new one, easily, without a scale problem, using PMP. Hey, I have newcomers. I have newcomers, this point and that point, this point. There are newcomers here. I can extract, since this information is already known, R1, T1, okay? From this one and that one, I can find R2, T2 as well. This and this will give you this one. Now, you can make a beautiful triangulation. New points. I can make a translation. I obtain the pose. I know the calibration K. Everything is available. Then I obtain this result, and I can increment all these things, and these newcomers, this guy, I don't know, the others, if they also have beautiful corners in the past, they are visible in the past views. If a majority, most of them, it's visible, I add these things to my model and I continue in this way. Okay, therefore, and a final result, 1, 2, 3, 4, 5, I don't know, after some batches, I simply run a bundle adjustment that I have explained. I refine my 3D structure and poses using this technique. Now, as you can see, I used features, SIFT, whatever. I match them. I solve F matrix, Hartley. I obtain E matrix. I decompose it, RT. I extract 3D triangulation, then make matches again. And then using PMP, I obtain the rotation and translation information, which is more reliable with respect to solving with E matrix, okay? And then I just start and I obtain new 3D points through this estimated here. I obtain this 3D structure between the I and I minus 1, the newcomers here, okay, sorry, the newcomers here. I obtain new 3D points. If they are visible in the past views, I put them into the model. The model is increasing, getting larger and larger. And finally, from time to time, I run bundle adjustment. Okay, that's how we do it. Okay, that's all from my side. That's the end of the E584 machine vision. Also, this chapter, I hope you enjoyed it. Hope to see you later.